So the remaining challenge here is to input two 32-bit signed integers from the user, calculate the difference, and print the result with all the bad input format checks and of course the checks for overflow conditions. Okay, so let's continue with this part. And instead of typing everything into this already very long program where we entered all of this, let's save this and modify it to adopt the existing code to use with 32-bit numbers right here. So my first step will be just simply to say file, save it as, and let's save this version of our program, preserve it as 8-bit sum solution, right? So we have this, hopefully this is correct solution, and we can save it. So then once we save it, of course we're not going to change it anymore, so the best thing to do is just to close it. And for now I can also close all other files. So let's go back to the Solution Explorer and bring back M08. And so now let's change this and change the existing logic, the logic that we already entered. And now instead of computing the sum of 8-bit values, now we're going to enter 32-bit values and compute their difference. So enter first 32-bit, right? So I'm just going to move along the existing code. Just make sure that you continue using m08.asm and not the file that you saved, if you'd like to use second solution in a separate file like I do right now. All right, so second 32-bit. So we need to input our 32-bit. I think let's use the split view like this. And yes, so we already have this prompt already that we can display. So now we're asking for the first 32-bit. So we have our buffer. We convert, assuming that this is a 32-bit int, convert it to EAX. If there was no overflow, we're going to be jumping forward, which means that conversion succeeded. By the way, that's misspelling right here, so we need to fix spelling here. So jump forward, and otherwise we're going to say that the input format, there was something wrong with the input format. Okay, now because as you recall, this macro A to D, if it succeeds, it converts everything to a signed integer, 32-bit signed integer. So as long as this succeeds, there is no need to check for any range. We can accept any value right here. So basically what I'm going to do is to get rid of this validation part. So when we begin our work with entering the first 32-bit, there is no need to check for the range. Any number is acceptable number. Okay, so we're just going to do this. So as soon as we detected that what the user just gave us right here in register EAX after converting it, we're going to accept it, and we're going to store the result, and now it's 32-bit size register EAX, and of course we're going to store it in first 32-bit signed double word. Okay, so we're just going to change this right here. Okay, so now enter first 32-bit supposedly is all taken care of. Now I'm going to just take what we have already here and copy and paste it to the second 32-bit, right? So entire section of the second 32-bit, I will start with what I did for the first 32-bit. So now this of course needs to change to second 32-bit, the same type of conversion, the same prompt for bad input. And so we have our second, again, we need to maintain the comment, 32-bit input ready, so we update the second 32-bit memory location with the result. And I think we also need to check this here and fix this comment, right? So copy and paste is nice, but it can be dangerous because it's so easy to have a typo or some other mistake. So just need to stay sharp and be careful about each step. And also here we have this enter second 8-bit, so this should rather say a second 32-bit, right? 32-bit. Let me see. Yeah, first 32-bit, then second 32-bit. So hopefully this is okay. Display the prompt, get result in EAX, converting this buffer into register EAX, prompting for bad input, jumping forward if everything is okay, jumping backward if we have a problem. So second 32-bit ready, store it. Now compute 32-bit difference, right? So we are going from 8-bit size register to 32-bit size register, so I'm just going to use EAX right here, and so everywhere we use AL, let's change this to EAX like this. And this also will be an EAX. So this also will be 32 everywhere we say 32. So that's 32, and it's no longer sum, it's the diff. Okay, so we have this difference, and of course to compute the difference we need to subtract. So let's compute the difference. Okay. All right, so let's see what we do in this portion of the program and see if this is all we need to change. At least let's validate this portion. So first thing that we do is that we take our first 32-bit and we load it into register EAX. Right, so this is the first step that we do. We load this into register EAX. So then we move this register EAX, it should say prepare difference for subtraction, another thing that we need to fix. Right, so we then move this register, the first 32-bit value back into the difference, and this is our starting point. Then we move into EAX the second 32-bit. Right, so we load register EAX with the second 32-bit, and then we take our difference and subtract the second one, the second number. Okay, so this looks fine. So these 4 lines, except of course we say prepare difference for subtraction. Right. Okay, we do that. And these are signed numbers. So to validate arithmetic overflow, we need to also update this comment and say if no signed overflow. And the signed overflow, of course, we check the overflow flag. And so we need to switch from jump if no carry to jump if no overflow. And the instruction, the conditional jump instruction for this type of flag is JNO, jump if no overflow. If no signed overflow, the overflow flag of course is used, we jump forward to display. Otherwise we're just going to report arithmetic overflow and jump all the way back to enter first 32-bit number. So another update, right? So this is a little tedious, so you have to be careful with all the changes. Hopefully this will be okay, right? But this is how we compute the actual 32-bit difference. And now we're going to display the 32-bit difference. Because we're going to be loading the difference, right? So this difference from here will be loading into the entire 32-bit EAX register. We don't need to reset EAX to 0 anymore. We can just grab it from here. And by the way, we probably don't need to do this move at all, because I think what we can do is that we can just use memory location as second argument for conversion this double word value to a set of ASCII characters in our special buffer for this, right? So say convert 32-bit sign integer to string. That's right, right? So our difference is a 32-bit sign integer. We convert it to string. Then we print the prompt. The prompt should say diff 8-bit, and that should be also changed to 32-bit to be consistent, right? So we just make this change, and then we display this prompt difference is, and print the result of the conversion in this D2A buffer. Remember, D2A stands for double word to ASCII. That's the macro that we use, and I like to name this buffer because I kind of like use this buffer with this macro. Okay, so that's a little buffer in memory which is in use by this macro. And so let's see if this all works fine. And this is the display. So hopefully if everything is correct in terms of syntax, we can build this program. So it builds okay, except it tells me that sum 32-bit, yes, there is no sum 32-bit. It should be changed to difference 32-bit. Okay, so we make that update as well. Okay, so this is the entire thing, and this is my code. I can show you the entire, this is the top portion of our program, right? So this is from the top to, say, the data segment. So the next portion of this program is from the data segment with all of the content of the data segment. Now we move to our main procedure. Inside of our main procedure, we begin with entering the first 32-bit number, and this is the logic. Then we enter the second 32-bit number, and this is the logic. And by the way, here these two labels are unused, so we could actually get rid of them, but I will just keep them the way it is right now. So then once we enter both 32-bit values, right, we proceed, so we're satisfied with this input, we proceed to computing the difference, right? So right below the input, the second 32-bit, we start computing the difference, and this is hopefully correct logic for that. We haven't tested it yet, but we are going to test it. And finally, we display the 32-bit difference by loading it, by giving a result of this difference and using another conversion to a string of characters. And we just display everything right here. So let's do some testing with these results. I press Ctrl F5, and now I'm about to enter this first 32-bit value. So let's try some kind of like error thing that is of course reported properly. So let's try something like 10 again. second 32-bit 20, and the difference is -10, which is quite nice.